This is one of my favorite types of problems to do with the Gibbs free energy equation. You can actually estimate the boiling point of a substance. It's not perfect, but it's pretty darn close, as you'll see, using the delta G equation. So we're actually going to be looking for a temperature, okay, because that's the boiling point. So if we wanted to write a reaction that would represent the boiling point of bromine, okay, you're only going to be dealing with bromine, pure substance. It is diatomic, so it's going to be Br2. And if you have it in the liquid phase, once it's boiled, you would have the same substance, but in the gaseous phase. So it's actually a physical process. Also, by definition, and you may not have learned this before because it's a little more complex than what we usually present in first year chemistry, but by definition, boiling point is the temperature where the liquid and gas are in equilibrium, meaning the processes are happening simultaneously at the same rate. We'll get into that way more in the future. But as you just heard, when you are in equilibrium, the value for delta G is 0. So we can set this to 0, and now all we need to get are the delta H values for this process, the delta S values for this process, and then we can solve for our T. So I'm going to get those values from your appendix in your textbook. So the next values you see are going to come from your textbook in the appendix. That's where I'm getting those values. So I plugged in the numbers from the appendix, and now we can do our algebra to solve for T. The one thing to highlight is that even though this value is 93, that's in joules over mole Kelvin. So we need to be consistent. So I just converted this to kilojoules, so 0.093 kilojoules per mole. Okay, so when I do my algebra, I get an answer here, and you should too, of 333. Your units there are Kelvin. Okay, so normally when we're looking at boiling points, we'll do it in degrees Celsius. So if you subtract 273 from that, you get an approximate answer. So I wouldn't say equals here, but approximately 60 degrees Celsius. And the literature value, or the accepted value, if you look it up, for the boiling point of bromine is about 50, that's not a negative, that's an approximately 59 degrees Celsius. So I just think it's so cool that this method, kind of works. You can also see that above temperatures of 333 Kelvin, the entropy is what is in control, and anything below that, the delta H value is in control. So you can kind of figure out the temperature where the prominence of entropy and enthalpy flip-flops. And that's also kind of what we just did here. When I say in control, I mean driving the reaction toward spontaneity, toward a negative delta G. We're looking at that as favorable, right? So 0 is kind of the point of inflection, but there are different ways to get a negative delta G. One where delta S comes more into play, and the other where delta H comes more into play.